Okay, so welcome to the panel discussion on quantum computing. I'm Andrew Childs. I'm a professor here in the computer science department, and it's my pleasure to introduce this panel. Quantum computing is an area that's seen a lot of interest recently. There's been a lot of developments toward actually realizing devices, and also a lot of interest in just understanding what are the capabilities and also what are the limitations of quantum computers. So my hope is that today we can have some discussion where we hear about this, what are quantum computers? What do we think they might be good for? What do we think they might not be good for? What is the role of computer science in understanding the power of quantum computers, and what does the future look like? So I'd like to just start by introducing Jake Taylor, who will moderate the panel. So Jake is a physicist at NIST and a researcher in quantum computing. He's a NIST fellow, and also through his role as a fellow of JQI, the Joint Quantum Institute, and QUICS, the Joint Center for Quantum Information and Computer Science. He's involved in the University of Maryland as an adjunct faculty member in physics and in UMIACs. Jake has really played a crucial role in not just doing research in quantum computing, but in kind of establishing structures that have helped the field move forward. He founded the Joint Center for Quantum Information and Computer Science that's really kind of brought a lot of attention to the computational side of quantum computing here at the University of Maryland. So I'm pleased to turn it over to Jake, and I'm looking forward to hearing the discussion today.
Thank you so much, Andrew, and thank you everyone for joining us today. This is, of course, a panel, which means that it's meant to be interactive. I don't have any awesome, beautiful visuals to show you, so it'll be a little more cerebral. But nonetheless, we, of course, gathered to have a conversation about the next 50 years, if we just have gone through the last 50 years of computer science at Maryland. And obviously, quantum computing is on that boundary between the future of science and the future of science fiction. And it's, of course, tremendously exciting to talk about the real opportunities behind it and some of the challenges ahead, as well as the interplay between quantum computing and other elements. I wanted to first actually just take a moment to go around and have my beautiful and educated panel to kind of talk briefly about themselves and where they're coming from. And then I'll start a bit of a longer dialogue. So again, my name is Jake Taylor, and I'm going to pass now to just going around to Ryan. Go for it, Ryan.
Yep. Okay. Thank you. Yeah, my name is Ryan O'Donnell. I'm a professor of computer science at Carnegie Mellon University in Pittsburgh, your neighbor here. And first of all, it's a real pleasure to be here. I gave a research talk yesterday at QUICS, and it's so great to come to an audience where it's filled with quantum computing experts. Almost every other place, I have to start out by explaining what is quantum computing from the beginning, and so it's really enjoyable to be here. So by training, I'm a theoretical computer scientist. I guess it's sort of is to computing as theoretical physicist is to physics. So in some sense, I mostly do math, and I think about the inherent nature of computation. And so at some point, I realized, from people telling me that, if you want to think about computation and the inherent nature of it, you have to think about all things that are doing computation in the universe. And since our universe is governed by quantum mechanics, it's essentially obligatory that if you want to understand computation, you have to understand quantum computation. So that's a little bit how I got into the field. And in terms of what I work on, one area of research which I don't work on so much is trying to use quantum computers to solve, the classical everyday computing tasks that we want to solve. What I'm more interested in is in the fact that, since we have a quantum world and quantum data, we need to develop algorithms and understand computation for inherently quantum problems. It's hard to learn from, probabilistic data, and it's even harder, therefore, probably to learn from quantum data. So how much harder is it? This is the sort of thing I'm interested in.
So I'm Daniel Gottesman. I'm a professor of computer science here at Maryland. I grew up in Maryland, actually, but I was at Caltech for my PhD, which was actually in physics. And at the beginning of the PhD, I started working on black hole evaporation and the information loss problem in black holes. And I got kind of frustrated with that because it depended on quantum gravity, and we have no idea what quantum gravity is. I mean, we have lots of ideas, but they're contradictory. That would be a better way of saying it. And there didn't seem any way to resolving that. So when Peter Shor came out with his factoring algorithm, which showed that quantum computers could solve some problems much faster than any classical computer, I decided to switch. and I've been working at it ever since. So one of my main research topics is quantum error correction and fault tolerance. So that's the task of making a quantum computer that's imperfect act like one that's perfect and lets us actually solve all these hard problems, despite the imperfection of the real devices.
Hi, I'm Scott. Is this on? Hi, I'm Scott Aronson. Like Ryan, I'm a theoretical computer scientist. I'm from the University of Texas, Austin. You know, I'm like to consider myself a friend of JQI and Quix, and I'm very honored to be here for this event. So. A lot of my work has been about the limitations of quantum computers, you know, the study of what we can't do with computers that we don't have. You know, I've also worked on learning of quantum states. I've worked on quantum money, copy-protected quantum software. So sort of different sorts of applications of quantum information. More recently, I've been interested in connections between quantum computing and the black hole information problem and things like ADS-CFT. I'm actually on leave for a couple of years right now to work at OpenAI on AI safety, which has basically nothing to do with quantum computing. But, you know, I tell people that for 20 years, sort of my job, and, you know, I should say I write a blog that's partly about quantum computing. And so that puts me in contact a lot with journalists doing quantum computing pieces who are asking me to, you know, explain quantum computing in one sentence. And, you know, I tell them, well, you know, I've been trying that for 20 years and can you give me 10 minutes? You know, I think I can more or less do it in that. But, you know, often I'm talking to people who have been sort of sold a vision that quantum computing is going to revolutionize optimization, machine learning, vehicle routing, and you know, and it's going to do all of that like next year, and you know, and they really believe this, and they're really hopeful. And I say like for a long time, my job was largely to tell people, you know, unfortunately, quantum computing probably can't help with your applications, or not anytime soon, and I can explain exactly why. You know, and then within the last year or two, my job has shifted to saying, yes, AI probably can help with your application, but I can't explain why.
Hi everyone, I'm Murphy New. I'm a new faculty just recently joined computer science, the assistant professor, like as of 2 months ago. So I'm extremely honored to join this prestige panel. In fact, just as of 6 years ago, I was in Scott's class in MIT, enjoying the chocolate pretzel he brings in every single class. So yeah, similar to Daniel Gottsman and Jacob, I actually had a physics degree in PhD, and starting off my PhD, I work on quantum optics, where our focus is not on quantum computing, but more on quantum cryptography. But as I was, you know, moving along in my PhD, I realized there's so much more unknown problem to be addressed in quantum computing, and really fascinated by this idea of so-called digital physics, which is if the universe is governed by physics and the most, you know, if we can formulate the universal computation problems, then all the physical problems can fall into this paradigm. Then solving physics problem is equivalent to solving a computational problem. And this paradigm is extremely beautiful to me, also because Seth Lloyd wrote a book about it. I love that book so much. And I had the opportunity to work with Google Quantum during my PhD, apply the funding from my advisor, and that's how I joined Google Quantum for after graduation. I have been working with them for past 4 years. So then I decided to switch from industry to academia, and I work on, because you know my background in industry, I work on the gap between very theoretical computer science algorithm and really detailed physics modeling of the system, where my interest and passion and research focus is to try to both think about how to deploy this fancy algorithm, Scott Ryan had been thinking about in the real most powerful and biggest quantum computers, but also like inspired by the physics of the hardware we have to think about what kind of algorithm we can develop to do error correction, to do learning, or to simulate quantum system. So that's my background.
Thank you so much. So I guess I'd like to just take a moment to center the rest of the conversation for our audience today. 10 years ago, computer science at Maryland had 0 hires in quantum computing. And Samir Kuler, who was the chair at the time, Amitav Varshini, who was the head of UMIAX at the time, and I'm not speaking loud enough. Right. So at the university, several key players whom you probably heard about last night and met, and myself sat down and asked, what is the opportunity for the Maryland Computer Science Department at 40 years old? And one of the answers was quantum computing. Simply recognizing that, as one of the progenitors of our field, Feynman, said famously, nature is quantum, damn it. And so we better understand how computation works at the fundamental level. That, of course, has led to a variety of really interesting results, many of which are negative, saying that there aren't that many differences, and some of which are positive, saying that there are some really important differences. And I think the recognition 10 years ago was that there's an opportunity to lay the foundational science for what computation can be. So we got together between NIST, my home agency, and Maryland, and formed a joint center, the Joint Center for Quantum Information and Computer Science, or QUICS. And now, of course, QUICS has grown 300% over the course of 10 years, and we'll have our, I guess, 10-year anniversary next year. But it's just been tremendous to see how, at 50 years, this element that was a glimmer in the eye of many computer scientists and of their interest 10 years ago has become much more central. And I think that it speaks to the universality of computing in our lives. So I just want to kind of put that foundational point in place. But I think a lot of our conversation today is actually zoomed in a little bit more on what the intersections are between these physical limits of computation and what people care about when they go home at night. And so we're not going to make that gap entirely bridged, but we'll do a little bit of our effort to just understand, what are going to be, for example, I'd like to start first with, what are going to be the opportunities that we can hope to learn from in the next 20 years? What are we hoping to learn about what computation can be at the quantum mechanical level? And so I'm open up the floor to my panelists here, and wants to start with that.
I mean, it seems clear that within the next 20 years, possibly sooner than that, people are going to try to build scalable, fault-tolerant quantum computers. And whether they succeed or whether they fail, we are going to learn something from that effort. When I joined quantum computing, in the late 1990s, it would have been, it was amazing, like worth a research paper if you could get 2 qubits to talk to each other at all. Right. And, a qubit being a quantum bit, the basic building block of a quantum computer. And, if you could only do this with, 50% accuracy, well, then, that was still pretty good. And so I've, as we've developed the theory of quantum computing to a sort of higher degree of sophistication, of course, we've also watched what's happened on the experimental side. And I think, back then there was very little for the theorists and experimentalists to say to each other because, the things people could realize in the lab were just so far from what we were contemplating as theorists. Okay, but if you look at with what accuracy can people do a 2-qubit operation, over the last 20 years, that 50% became 90%, became 95%. If some of you have read about Google's claimed demonstration of quantum supremacy back in 2019, they had like 53 qubits and about 1,000 operations on them with about 99.5% accuracy. And within the last year or so, various groups have been talking about 99.8 or 99.9% accuracy. So our best guess from the theory of quantum fault tolerance or error correction, we don't really know, and maybe Daniel will have more detailed opinions here because he's the real expert here. But if you could get, let's say, 99.99% accuracy, so just one more 9 there, then we know quantum error correcting codes that look like they ought to start to be practical. Maybe you would need a whole building full of dilution refrigerators, just like the first classical computers, filled a whole room or a whole building. But if you wanted to factor, a 2,000-digit number and thereby threaten most of the public key cryptography that currently protects the internet, then once you get past what's called this threshold for fault tolerance, where your components are reliable enough that you can correct errors faster than you're introducing new ones, then it's all just a question of how much do you want to scale it up, and how much money do you have to spend on that? And so, we are going to see that effort either succeed or fail. Now, I have some colleagues, both in computer science and in physics, who have adamantly believed that building a quantum computer is impossible, that it can just never happen, that either we just don't understand quantum mechanics, or maybe quantum mechanics itself is wrong. But this prediction of quantum computers is just too absurd to be believed. And what I always say to those people is, well, I hope that you're right, because if you're right, then that's a revolution in science. Right, that overturns what we currently believe about physics, and maybe the biggest way in 100 years. Okay, whereas if we're right, we can merely build a quantum computer and it works like the theory says with enough effort. That is the more conservative possibility. Right, that's kind of the more standard thing that could happen. But one way or the other, I think that in the next 20 years, we're likely to find out.
Murphy, do you want to talk a little bit about what that room full of dilution refrigerators might look like, and what are the challenges to get to that first big computer?
Yeah, definitely. In fact, Google just opened their new campus in 2020, where they built a specific building dedicated to rooms of dilution refrigerator. And in fact, there's so many dilution refrigerator, we have to code them, like there's a pink, red, blue, yellow, and then we run out of color. I have to add name of trees like willow or whatever. But anyway, so it's extremely heavy engineering endeavor. And for example, like looking at 20 years, like Scott pointed out, there is fundamental question that need to be addressed, because all the theory we know so far in regard to scalability are at the infinite system level. Like theoretically, we can prove are all at infinite system level. But what we have are finite system. We will never have an infinitely big quantum computer. So we're really dealing with 2 different regimes of physics and computer science. In particularly, because we're at the finite regime, there's like a huge factor, a scaling factor that might not be scalable, but that can prevent us really seeing the fundamental predictions from computer science. For example, the quantum supremacy demonstration, it took us 3 years to get from the theoretical proposal to the experiment, because we can't really be confident enough that we did the best we can to have the best coefficient in front of whatever scaling we're demonstrating. And same with error correction, where a lot of engineering effort that's really gonna be needed to pour into the next 20 years to show that we have done everything we can that physics permit us to push to the limit of the best we can to see how the scaling really works. And I believe there's a huge opportunity, in fact, in the next 20 years, as we really start switching from, this effort of envisioning things to doing things, there's a lot of things we can use a classical computer to help quantum engineering, as opposed to like competing with a classical computer. And in fact, we have already seen so many areas of different level of quantum stacks, from hardware architecture design to quantum control to quantum calibration to the final benchmark of the whole application. Every single layer, we have seen more and more application of classical machine learning in there to really push it to the extreme level of capacity. And I think we're only starting that. We haven't really seen, for example, the power of large language model in quantum computer design, or even in the fundamental theorem proof, like proving P equals to NP, like recently claiming archive preprint. So yeah, I'm excited to see this collaborative effort between the classical side of computer science and the rising side of quantum computer science to really answer the fundamental questions in the next 20 years.
Yeah, so I guess I kind of want to actually maybe follow up that a little. Maybe Ryan, I could pass to you to the question. What is the intersection between classical computer science and what quantum is looking at, or what the opportunities look like there?
Yeah, that's a great question. I think this is on. Yeah, that's a great question. It's one that interests me a lot because there's something I feel like a little bit magical about quantum computing and quantum mechanics. It seems to intersect a lot with other areas of research which you wouldn't necessarily expect. And there's many instances. In fact, I was talking just about one yesterday where people working on quantum computing actually just discovered new facts about regular old classical computing. So to take a good example, there's an enormous breakthrough last year in the field of designing quantum error correcting codes by two people, Panteleev and Kalachev. And they designed like a new, sort of most efficient quantum error correcting code. It's very theoretical, so maybe not too practical right now, but maybe with like a level of trade-off between accuracy and overhead that was not thought to be possible at first. And so this was a tremendous breakthrough. And funnily enough, at the same time, there was another breakthrough in classical error correcting codes, the design of locally testable codes that had been long sought out for decades. And that was solved by some classical researchers. And at the same time, these quantum researchers who designed the quantum error correcting codes, they got the same classical result just as a byproduct. They almost accidentally solved this open problem in pure classical computation. And this is a funny thing that seems to happen over and over. Like the study of quantum computation has given us really unexpected benefits in in pure math, in the foundations of physics, in basic problems in classical computation. So it's one thing I really like about it. There seems to be something magical about quantum computation as an area.
Actually, speaking of those codes, maybe I could pass to Daniel, because of course you predicted the existence of these codes about 10 years ago, give or take. And I'm kind of curious, what is it?
Yeah, that's not completely accurate.
You can correct my statement.
Yeah.
But I'm kind of curious though, in terms of the changes from 10 years ago to today to 10 years from now, what are we looking at for the landscape of getting to practical machines?
Well, I mean, so the big thing is the improvement in the experimental error rates. Because, as Scott mentioned, if the error rates are too high, then the errors are occurring faster than you can correct them with your error correcting codes. And if the errors are low enough, then you can win. And actually, 3 nines is probably enough. So that's 99.9% accuracy. So we're kind of at that level now. But to make that work, everything else has to be right. I mean, you have to be able to do that in a big scalable system, and you have no errors that are causing multiple qubits to go wrong at a time, things like that. So having lower error rates just gives you more breathing room, and also reduces the amount of extra work that you have to do on error correction. The other thing that's happened in the last 10 years is there's been quite a lot of progress on the theoretical side. in terms of, again, how much extra work you have to do error correction. So at the time, I think it was the case that the family of codes called the surface codes were leading candidates. They're still leading candidates today, but people have come up with much better ways of doing them. So reduce the number of extra qubits, reduce the amount of work you need to do error correction. All that stuff has improved quite a lot in the last 10 years. But I've advocated a different approach using something called low density parity check codes for fault tolerance. Now, this big open problem that was solved is also about low density parity check codes. It's not specifically about the fault tolerance. So it was a problem that was known as an open problem going back longer than this. But it's certainly very exciting in its own right to solve that open problem. And as Ryan said, it had this kind of unexpected benefit of connecting to this classical problem. And moreover, it had another unexpected benefit in the field of quantum complexity theory, solving another kind of open complexity theoretic conjecture, which in itself was kind of a stepping stone to an even bigger conjecture, which is not solved. But that's how you make progress, right? Steps. So we're still not at the point where we can connect the theoretical end of dreaming about the fault-tolerant protocols we can do with the experimental protocols. And like Scott, I think and hope that we'll get much closer to connecting those and maybe actually connect them in the next 20 years. Again, it's always slow progress. From somebody that's in the field, it always seems like, oh, well, I thought they would do this fault-tolerant demonstration years ago. Why haven't they done it yet? And partly that's because as a theorist, it's very easy to write stuff down, and as experimentalists, they actually have to build something and get it to work.
Maybe some context for those of you who aren't familiar with this interplay between devices that don't quite work and an algorithm that you want to run. It's just worth mentioning, and I think maybe Scott's on the record about this, that we haven't really discovered the transistor of quantum computing. So the level of accuracy that we keep talking about has to do with the fact that the operations that people can do in their laboratories and in their devices is not nearly as reliable as a transistor that you take for granted, honestly. So I don't know if you want to kind of.
So often I get people saying, well, it's been 40 years now since Feynman, was talking about quantum computing. It's been 30 years since the discovery of Shor's factoring algorithm, which really made this into a field. Why don't we have quantum computers yet? What is taking so long, right? Hasn't this just been a big disappointment? And I like to contextualize it by saying, look, how long did it take from Charles Babbage, thinking about classical computing in the 1820s until the invention of the transistor, which really made it practical, right? That was more than a century. Okay, so, and in fact, the reason why Babbage couldn't do what he wanted was mostly precision. Machining precision. He just couldn't build parts that were accurate enough with the technology that existed at the time. So, I think, that is the situation with quantum computing. I think that, optimistically, we have now maybe entered we're starting to enter the vacuum tube era of quantum computing. But what we really want is to be able to scale to as many qubits as you like and as many operations as you like, and have the qubits stay alive, that is, maintain their superposition state for as long as you need them to. Okay, that is the dream of quantum error correction. And if you're only halfway there, it's kind of like having half of the critical mass for a nuclear chain reaction. It doesn't give you half of the explosion, right? So that's sort of been the engineering agenda, for the last decades. But I think, if you think of, developing these sort of utterly new technologies on the scale of centuries, well, I hope that we can do this in less time than it took for classical computing.
Maybe I'd like to add to Scott's point in that I think there's another thing that we can also take into account when we're comparing this type of difference of transistor versus quantum computer, in that if you calculate how long you can compute and how fast the error happen in classical computer, you're talking about 1 error per 2 years, because the cosmic ray hit one of the transistor, exactly the transistor. And you can compute like running a machine learning model for like days. And then compare that to a quantum computer. How fast can we run gate? It's limited by the fundamental interactions. And so it's limited to, for example, around 20 nanoseconds to run a meaningful operation. And then, but we can run a quantum computer, without error correction indefinitely. And we're looking at around 10 microsecond runtime. So for every 10 microsecond used for computation, we have like error happening at the magnitude of 10 to the minus 3. And so after you calculate, you realize there's a 14 magnitudes of difference between the ratio of error rate in the, over the computation rate. And so then maybe we want to ask, is this difference fundamental, or is this difference only purely engineering? And it's possible it is fundamental, and then maybe we have to really think about different way to program quantum computer based on the fundamental physics difference. But this is of course open question whether this is inherent or this is superficial.
Yeah, I guess this kind of does bring up a side point, which may or may not be apparent, but there's of course these engineering tasks, but then there's also this sort of questions about the universe, right? And maybe I know that the computer science department here doesn't just do computer science, right? It's also computer science and bioinformatics and computer science and natural language processing for things that matter to people. So I'm kind of curious if we could maybe look a little bit more at these questions of what are the fundamental questions that computer science is going to uncover about the universe as we try to build these things and try to build them better. So I know we have some thoughts already expressed. If anyone would like to dig in on that a little bit more, I'm happy to hear it.
So, I mean, actually, that's kind of the origin of quantum computing, which is it has its kind of prehistory before it was actually quantum. In Rolf Landauer studying a paradox known as Maxwell's demon. And so in physics, there's this principle of the second law of thermodynamics, which says that entropy has to always increase, that things get kind of less ordered over time. But Maxwell suggested that, well, what if you had a teeny little demon, which you can think of as a little computer? He didn't know about computers back then, but a little computer that on the atomic level would look at each atom and say, this atom is fast, I'm going to put it over here. This atom is slow, I'm going to put it over here. Then you'd be separating the fast atoms from the cold atoms, which is something that should not be allowed by the second law of thermodynamics. So this seems like it should be impossible, and yet it also seems like it should be possible, right? Now, particularly nowadays when you can imagine sorting individual atoms. And so Rolf Landauer studied this, and what he discovered was that, yes, you could do that, but if you had a computer that was doing it, it would, in its memory, know where the atom came from, right? And so you wouldn't actually be decreasing disorder. It's just you'd be moving it from the disorder of the atoms into the disorder of the memory of the computer. And that understanding that led him to suggest that it was actually erasing bits that caused entropy and resetting your computer. And so that line of thought, and so he had this this motto that computation is physical, and that sort of line of thought was kind of what inspired a lot of the quantum computing, the early quantum computing research. That if computation is physical, then the nature of computation should depend on the underlying physics, and that's something that's kind of been borne out. And one of the fundamental principles of at least theoretical computer science is this Church-Turing thesis that all computers can solve the same problems. And it's been strengthened to say that actually all computers can solve the same problems in roughly the same amount of time, right? And this is something we experience in everyday life, right? You have software, maybe it runs on a Mac, maybe it runs on an iPhone, maybe it runs on a Android or Windows machine, but we always believe that that software can be translated from one device to another. And the first thing that quantum computing told us was that's not true anymore. That if you can build a computer out of single atoms, then now there's new algorithms that cannot be run on any of these classical devices. And that can give you a big improvement. So that's like a fundamental fact about physics that we discovered studying quantum computing. And it's also a fundamental fact about computer science.
Yeah, that's a great answer. And I want to try to tell a little anecdote about another big breakthrough in quantum computation research that has a similar, I think, a story. The breakthrough goes by some like complicated acronym, MIP star equals RE. So I'll do my best in like 1 minute to explain what this means, because I think it's quite similar to what Daniel was talking about. So I guess one thing that every computer scientist knows about here is Turing's theorem, which basically about the unsolvability of the halting problem, which basically says like if I give you a sheet of paper that has some code written on it in Python, and I ask you the following task, if I run this code, how many steps will it run for? Or will it run for infinitely many steps because it gets into an infinite loop? This task is known to be unsolvable by any algorithm. So if you can put a pin in that in your mind, this recent discovery was about some kind of analogous thing in physics. So last year, the Nobel Prize in Physics was awarded for an experiment that was done in the 80s and studied first in the 60s about proving quantum entanglement. And there's an experiment that you can do that basically works. It's, something you do on your table. It works if you put like 2 entangled qubits or 2 entangled particles into it. And it doesn't work if you put in unentangled particles. So then if you do the experiment and it works, then you've got evidence that you can really have entangled particles that are far apart. You can design more sophisticated experiments that like have the feature that like sort of they work if you put in 4 entangled particles, 2 here and 2 here, but maybe they don't work if you put in 2. And you can design more refined ones that work if you put in 6 entangled particles, but they don't work if you put in 4. So then you can ask about this task, if I give you the description of an experiment like this and say, how many entangled particles would you have to put in order to make it work? Or would you need infinitely many particles entangled to make it work? How complicated is that task as an algorithms problem? And this breakthrough showed that it was also uncomputable. There's no algorithm that can solve this problem. And besides, resolving some open problems in mathematics, it really resolved some open problems in the foundations of physics. And it really came about through a computer science perspective of, thinking about, Turing machines and computations and so forth in the context of fundamental physics.
I mean, if we're doing vignettes, I think one thing that's been relatively underappreciated about this field is just the way that the language of quantum computing and information, has been, incredibly powerful for just talking about physics, talking about condensed matter, about even, quantum gravity, and this is been an impact that it's already had, before we even have scalable quantum computers. So it is within the last decade, it's almost completely transformed the discussion of the black hole information problem. To take one example, so this is the problem that was raised by Stephen Hawking in the 1970s when he said information that falls into a black hole seems to get destroyed. And eventually, as Hawking also discovered, black holes do radiate out, their mass right into Hawking radiation. But the calculation that he did suggested that the radiation coming out of the black hole is completely uncorrelated with whatever fell in, right? Or almost completely uncorrelated. So it looked like black holes are just trash cans of the universe, right? They just delete information. And this is a real problem if you believe in the universality of quantum mechanics, because one of the basic principles in quantum mechanics is called unitarity. And it basically says that information should be, neither created nor destroyed, right? The evolution of quantum states should be reversible in time. And so people have, thought a lot about this over the decades. And then, in the and they thought that they had a semi understanding of what was going on that involved something called complementarity that said, it depends on your perspective. The person inside of the black hole has a different view from the person outside the black hole. But as long as they can never, meet and compare notes, then maybe everything is okay. But then in 2012, there was this thing called the firewall paradox, which said, no, if you take seriously that the information that falls into a black hole has to come out in the Hawking radiation, then there is an experiment that someone could do by waiting outside of a black hole, collecting all the Hawking radiation that comes out, routing it into a quantum computer. And you'd have to wait for the black hole to mostly evaporate. So if it had the mass of the sun, that might take about 10 to the 67 years. Okay, so you assume that you have a really long grant. Maybe Jake could help in arranging the funding for this. Okay, but but then you would make some measurement that tells you something about the Hawking radiation, and then jump into the black hole. And then you reach a prediction that you should just burn up, encounter an end of space-time right at the event horizon. Right? And to be clear, everyone agreed that you should encounter an end of space-time at the singularity. Okay, but the event horizon was supposed to be a relatively ordinary place, at least as you're passing through it. And this said no, and this was a big problem for our understanding of, quantum field theory, general relativity, what were considered like very well settled areas of physics. And so people had, enormous arguments about this. But one of the most striking things that was said came from Daniel Harlow and Patrick Hayden, and they said, well, how hard would it actually be to do the quantum computation that is called for by this experiment, right? And they gave some evidence that it would actually be an exponentially hard problem even for a quantum computer, which means you couldn't do it in a mere 10 to the 67 years. Okay, it would take, even with a quantum computer, it might take like 2 to the 10 to the 67 years. Okay, and so then the black hole would have long ago evaporated, before you'd even made a dent. And so then you can't jump into it. And so maybe there's no problem. So, this was a new thing, that computational complexity seems like the armor that is sort of protecting the geometry of space-time. And, they used, to argue for why the problem is hard, they used a result from my PhD thesis, right? That was the thing that forced me to start paying attention to this. And, even though all my training is in computer science, I have astonishing, ignorance of a lot of things in physics. I became a sort of computer science consultant to the quantum gravity theorists. And this is just an amazing bridge that's been built, between fields. And, these are the sorts of things that would not have been possible if we didn't have the language of quantum computing and information.
Actually, maybe just to follow up on that briefly, of course, one of the things that we've done at Quicks is develop a curriculum that uses the language of qubits, which allows physics graduate students, computer science graduate students, and also electrical engineering graduate students to all take the same class. And the sort of simplicity of reducing things down to qubits has been super valuable. But I'm kind of curious, maybe I know, Murphy, this was on your mind earlier. I'm kind of curious, what is the advice that we have about how, as you become interested in quantum computing, what needs to happen on the education side to bring people in the door, and to both people just getting started, but also people who are already advanced in their understanding but want to think about the space?
Yeah, I definitely have experience having, at Google, I have a lot of interns coming in that's of pure computer science background. And I think one of the first thing it would really help is to have a better understanding of a better bridge between the theoretical education that I've been having with the realistic system that we're considering or we're trying to build. So that means we need a more interdisciplinary approach where we also want prepare physics students with better computer science background. And so this, I think, maybe I'll just jump back to the fundamental question as one example. One of the fundamental open question that also already helped quantum computing is how does superconductivity work, high temperature superconductivity, and low temperature superconductivity. Like how does this magic happens when all the atom, and in fact, this is a very first macroscopic, one of the very first macroscopic quantum effect, where it's what we're trying to do in quantum computer. We want to build a macroscopic, large scale quantum system, but somehow nature already did it, where if you cool a metal down, almost all the metals on the periodic table, and some of them you have to apply some pressures in addition to cooling it down. Then under that condition, magically all the atoms of this metal start to work with each other such that they interact with all the electrons around them in a very cohesive manner, where everything is in tune and synchronized and described by this type of Cooper pair phenomena. And this type of superconductivity have been discovered and used in computing far before quantum computers, like superconducting logic, also used in astronomy. And but doing this type of quantum computing engineering and quantum computer design forced us to think about this microscopic effect in the context of computing. What can we learn from that? What can we use it? For example, we can use that effect to build a nonlinear oscillator to encode a qubit. But I think for most computer science students, when I talk about superconductivity, I only mean like a 1 hour introduction in physics. But I think on the other hand, if all the computer science students are comfortable with some basic EM field theory, then just from Feynman's lecture notes, you don't need to know like quantum field theory to understand phenomenological superconductivity. And that might really help, I think, the next generation thought leaders and researchers to think about really what's next at the intersection of physics, electrical engineering, computer science, and mechanical engineering.
Thank you.
Something about education?
Actually, I did want to open the floor to the audience because we're down to the last 10 minutes. So if you can keep 30 seconds, you're welcome to. Otherwise,
I'll just say really quickly, following on with what Murphy said, if you're interested in quantum computing, it's easy. You can get into it. I teach an undergrad course about quantum computing at Carnegie Mellon, and I really try to simplify it as much as possible. And by now, there's no complex numbers, there's no matrices, but we still do like the factoring algorithm and Grover's algorithm and everything. And we play around with quantum computer simulators that are written in Scratch. So anybody can get into it. So give it a try.
So I'd like to take a moment and open up the floor now to the audience and your questions. I see one in the back and then one on the side. And of course, and one on the right. So we only have 3 microphones. So I will, I'm going to walk it up. Thank you. Can you pass it along when you finish?
Hi, wonderful panel. Thank you. So I appreciate the conversation about the feasibility of actually seeing quantum computing in practice. Coming from an industry perspective, in the opinion of the folks on this panel, are we looking at kind of a Y2K moment where anybody who's not using post-quantum crypto techniques is essentially owned, right? Is that coming, or is that hype?
Well, I mean, Y2K, we knew exactly when it was happening, right? So that's
Right.
one difference. But I think that there is a strong case for already thinking right now about migrating to quantum resistant forms of encryption. So some people might know that NIST had a 5-year-long competition to agree on standards for post-quantum encryption. Some crypto systems got sort of worryingly far along in that process before they were just completely broken. Okay, but there are the class of crypto systems that most of us thought from the beginning you would want to move to in a world with quantum computers are ones based on high dimensional lattices. And those are indeed the ones that have won this NIST competition. And now begins the sort of massive social and engineering effort of getting everyone to upgrade all of their web servers and their routers and all the whole infrastructure of the internet to use these post-quantum crypto systems, right? And they do require larger key sizes to get the same level of security. So there are going to be and anytime you switch to something new, there are new side channel attacks that become possible. So there are going to be a lot of headaches. Okay, but certainly if you have it's hard for me to speak because I don't even have any secrets worth talking about, right? But some people do, right? If you have secrets that need to stay secret for 10 or 20 years, then I mean it would be shocking if various intelligence agencies around the world were not already vacuuming up data that's encrypted in the hope that they will be able to break it later, using a quantum computer or using whatever else. And so you might already want to be using post-quantum cryptography now, if you have things that need to stay secret over that kind of time scale.
In fact, speaking as a member of NIST, I can say that we encourage everyone to make the transition by 2030 and have a lot of resources available on the web if you want to get more details. I think we have another question over here. Yeah, no, you're holding the mic.
So, sorry, if, this may not be directly related to quantum computing, but it's indirectly related. Has any of you seen the documentary, The Social Dilemma? So it talks about one of the effects it talks about is how it affects human interaction and how much notifications we get and how much the social media applications affect us in the sense. So my question is, 30 years ago, we didn't have this thing, smart computer. Now we call it a smartphone. But anyway, if you watch The Social Dilemma, you will see the effect of it. My question is, at the rate the information is coming at us, humans, what is your take on as far as the speed at which the information is coming in and how it's going to affect us humans on a daily basis? Thank you.
So one thing that's kind of funny about quantum computing is that it probably won't be very visible on a daily basis to most people. And the reason for that is that quantum computing lives in this kind of alien world of single atoms that can be in superpositions of multiple things at a time. And so you need an interface of a classical computer to connect to what regular humans can perceive and do. And so while it's possible, I mean, probably not in 20 years, but it's possible someday quantum computers could be miniaturized and made to work at room temperature. You don't need those rooms full of dilution refrigerators. That the effect that will have is that some problems that today would be very hard might not be hard anymore. And the thing is, we don't actually know what those problems are. I mean, some of the things that we know quantum computers are good for, factoring large numbers, breaking current day encryption schemes. Most people are not going to want to do that. Simulating quantum systems, that's really useful in anybody building stuff out of atoms, making chemicals, things like that. But again, it's not something that most people want to do in their everyday life. What else? We don't know. And part of the reason we don't know is we don't have the big computers, quantum computers yet, to actually try out algorithms. So the only algorithms we know will work are the ones where we can mathematically prove that they work. And that's only a small scope of all the possible algorithms. Like today's machine learning algorithms, we can't prove that they work, but they do, right? And people are proposing lots of quantum machine learning algorithms. But again, we don't know if they're going to work until we actually have the big quantum computers to try them. So exactly what impact it'll have on people's everyday life is really just impossible to predict at this point.
In the 1980s, Galois field theory was used for error correcting codes for digital signal processing, and you mentioned error correction for quantum computing. Is it possible to give sort of a high-level description of what an error correcting algorithm would be for quantum computing?
Yeah, I guess I have to answer that one. So, yeah, so the simplest classical error correcting code is called the repetition code, right? You have a bit, 0 or 1, you want to protect it, you repeat it 3 times, say, 0, 0, 0 or 1, 1, 1. Then if one of those 3 bits goes wrong, you can see that it's different and that the other 2 are probably the right ones, right? It's more likely that 1 bit went wrong rather than 2 bits. So quantum computers, that doesn't quite work for 2 reasons, 2 main reasons. So one of them is that you're not allowed to look at the states to see what they are. Because if you do that, you'll destroy the superpositions that make them special in quantum. So you have to be careful and arrange things so that you only learn about the nature of the error and not about the state that's encoded, the information, the quantum information. Yeah, and the other aspect is there's more things that can go wrong with a quantum state, but otherwise it's kind of similar. Last question.
Okay, thank you. So you know the technique randomized rounding in combinatorial optimization? So I was wondering, since a lot of quantum computing relies on superposition and entanglement between qubits or discrete random variables, can randomized rounding algorithms, their accuracy be improved on quantum computers?
I guess the short answer is yes, something can be improved. If we have, this is presupposing we have full-scale fault-tolerant quantum computers, but roughly speaking, there's these algorithms of like Grover's algorithm that basically say if you have any kind of randomized algorithm that works with high probability in a certain number of steps, and roughly speaking, you can use a quantum computer to get the same level of accuracy and square root the number of steps. So it's not an exponential speed up, but generally most kind of randomized algorithms that work in this Monte Carlo way can have some improvement.
So I need to apologize because we are actually out of time, and I'm happy to continue the conversation after. I want to take a moment though and thank the panel so much for your deep insight and thoughts. Can you join me in that, please?